Hey everyone, welcome. So today we're going to tackle one of those classic coding puzzles. You know the kind, it looks super tricky at first, but it all comes down to this one really cool insight. Let's just dive right in. All right, so check out this set of numbers, 1, 5, 11, and 5. The question is pretty straightforward, right? Can you split these numbers into two separate piles where each pile adds up to the exact same amount? Pause for a second and think about it. It's a fun little brain teaser. We're going to break this whole thing down step by step. Okay, so here's the game plan for today. We'll start by really nailing down what this puzzle's all about. Then we'll hit that one key insight I mentioned. After that, we'll pull out the big guns, dynamic programming, and build a table to solve it. Of course, we'll walk through the code, see what the final answer actually looks like, and then talk about why this whole thing even matters. Sound good? Let's go. All right, first things first. Let's get on the same page and formally lay out the problem we're trying to crack. What are the actual rules of the game here? So here's the official textbook definition. You're given an array of numbers. Your entire job is to figure out if you can split it into two subsets, where the sum of each subset is identical. That's it. It's just a yes or no answer. And the key rule? Every single number has to be used, and it can only be in one of the two piles. Okay, now for my favorite part, the aha moment. See, when you first look at this, you might think, oh man, I have to check every single possible combination of these numbers. And yeah, that would be incredibly slow. But there is a brilliant shortcut that cuts right through all that noise. To see it, let's just look at a different set for a second. Let's say we have 2, 7, and 4. Simple enough? What's the total sum? Well, 2 plus 7 plus 4, that's 13. Now, just think about that for a second. Can you split the number 13 into two equal whole numbers? Right? No way. You'd end up with 6.5 for each pile. And we can't do that. We're working with whole numbers here. So what does that tell us? What's the absolute first, most important check we should always make before we even think about writing some complex algorithm? And that is the core insight. It's so simple, but so powerful. If the total sum of all the numbers is odd, it's literally impossible. Game over. You can just return false right away. But if the sum is even, the problem completely changes. It transforms. We don't have to worry about finding two subsets anymore. We just have to find one single subset that adds up to exactly half of the total. Think about it. If we find that one subset, what's left over has to add up to the other half. It's guaranteed. Okay, so let's bring that back to our original problem. We have 1, 5, 11, and 5. Add them up, and you get 22. That's an even number, so partition might be possible. We don't know for sure yet, but the door is open. And thanks to our insight, our goal just got way simpler. All we need to do now is find any combination of these numbers that adds up to exactly half of 22, which is 11. That's our new target. So how do we find a subset that adds up to 11? Well, again, we could try every combination, but that's the slow, brute force way. Instead, we're going to use a really powerful technique called dynamic programming, or DP. The whole idea behind DP is to not be wasteful. We're going to build a table that kind of acts like a memory. We solve tiny little subproblems first, and then we use those answers to solve slightly bigger problems, and so on, until we've solved the whole thing. And this is what that table looks like. Now, I know DP tables can look a little intimidating at first, but trust me, the logic is really simple. The columns, those just represent all the possible sums we might want to create, all the way from 0 up to our target, which is 11. And the rows, they represent the numbers from our array that we're allowed to use. We'll start with none, then add the first number, then the first two, and so on. So every single cell in this grid, let's call it DP of I, j, is just going to hold a simple true or false. That's it. And it's answering one very specific question. Is it possible to make the sum j, the column, using only the first I numbers, the row? Our whole job is just to fill this table out, cell by cell, until we find the answer we're looking for. So how do we actually figure out if a cell is true or false? Well, for any given number we're considering, we really only have two choices, right? Choice 1, we don't use the new number. If we don't use it, then the only way to make the sum is if we could already make it with the numbers we had before. So we just copy the answer from the cell directly above us. Easy. Choice 2, we do use the new number. If we use it, say the number is n, then we need to have been able to make the remaining sum, which is j minus n, using the previous set of numbers. So we look in the row above at that other column. And here's the kicker. If either of those choices works, if either of them is true, then the answer for our current cell is true. Okay, That might sound a little abstract, but this two-choice logic translates perfectly into code. Let's take a look at how we'd actually tell a computer to build this table for us. And really, it's just a couple of nested loops, nothing fancy. The outer loop just goes through our numbers one by one. The inner loop goes through all the target sums we care about, from 1 all the way up to 11. And right inside there, that's where we'll put that simple two-step logic we just talked about. Can we make it without the number, or can we make it with the number? And as that code runs, it just starts filling in the table. True, false, true, false. Let's just trace one real quick to see it in action. Let's say we're trying to figure out if we can make the sum of 6. And right now, we're allowed to use the numbers 1 and 5. Okay, so we ask ourselves our two questions. Question 1, can we make 6 without using the 5? Well, we look up one row, and nope, that's false. Okay, on to question 2. Can we make 6 by using the 5? All right, if we use the 5, we need to have been able to make the leftover amount, which is 6 minus 5, so 1. Could we make a sum of 1 with the previous numbers? We look up to the row above, in the 1 column, and yes, it's true. Since one of our options worked, this cell becomes true. And it makes sense, right? We can make 6 using 1 plus 5. So, after our loops chug along and do their thing, our entire table is filled out. It's basically a complete map of possibilities. And the answer to our original big question, it's just sitting there, waiting for us in one very specific cell. And there it is, the bottom right corner. This one cell answers the final question, can we make our target sum of 11 using all the numbers available to us? And the answer is true. It worked. A partition is definitely possible. Now, the table just tells us true, which is great, but what are the actual piles of numbers? Well, you can actually backtrack through the table to figure that out. And in this case, it turns out one subset is 1, 5, and 5, which, yep, adds up to 11. And what's left over? Just the number 11 by itself. So we have two subsets, both equal to 11. A perfect partition. So satisfying. So, okay, we solved this one little puzzle. Cool. But what's the big deal? What's the real takeaway here? Why do we go through all this trouble with tables and loops? Here are the key things to stick in your brain. First, that shortcut is huge. Always, always check if the total sum is even. It can save you a ton of work. Second, remember how we reframed the problem? We changed it from finding 2 equal piles to just finding one pile that equals half the sum. That simplifies everything. And finally, this is the big one. Whenever you see a problem that's about making a series of choices to hit some kind of target, your brain should start whispering dynamic programming. It's just such a powerful pattern for remembering solutions to smaller problems so you can solve the big one efficiently. Look, this was never just about splitting numbers into piles. This is a fundamental pattern. It's the key to solving a whole class of problems, sometimes called knapsack problems, where you have to pick and choose items to reach a specific goal without going over. So I'll just leave you with this question. Now that you have this pattern in your toolkit, what other problems that seemed impossible before, could you now break down and solve? Think about it. Thanks for hanging out with me today.